Yes, good morning, everybody. Today we are going to start with convolutional neural networks. So, neural networks, they were introduced basically for the image processing. So, first question which arises, why when we revisited artificial neural networks, ANNs, because the GPU or the computational capabilities, they were scaled up, then why for images, we still have to look for convolutional neural networks. So the biggest challenge to this was that for the fully connected networks, that is our ANNs, the typical MLPs, what we are using, they are fully connected networks, and the scalability with them was an issue because you can just think that if the image size is 224 into 224 into 3, the three color channels, it is a colored image. So it means fully connected layer would have one 15 1,50,529 parameters which need to be trained. And this is for a single layer. So just think normally for the hidden layers, we go with the number of neurons either equal or higher than the previous layer. So if we go by that parameter, it means even if I have two hidden layers, it will be having training of these many parameters at least minimum. So that is a big problem, even if we are having the GPUs with the computational speeds of gigahertz. Okay, so that was a challenge. So there was a need where we had to think of an alternative. So here the image was broken down, sparsity of the networks, it was exploited. How do we exploit it? The weights, they were distributed among a section of image. So we can think that there are certain regions of the image which we are mapping to our next layer, and the weights, they are coming from the distribution over the entire region which we are mapping to a neuron in the next layer. So this was the idea behind convolutional neural networks. So it just works as a filter in which certain properties, they could be uh, from the image, they could be captured. So basically feature extraction could be done through the convolutional layers. So number of filters, they have to be applied. There's not a single filter. Let's say for edge detection, we have one type of filter. For graying of the image, we have another type of filter. So different for sharpening, we have another kind of filter. So different type of filters, they are applied to the same image over the same regions, and their response, actually it is extracted as a feature map. And these feature maps, they are collectively composing a volume of collected filters over the entire image size, and they are being used or convolved together to get the important features using the sparse connections rather than each and every pixel being mapped to the neurons. So yes, as I told you, it is volume. So it means there's a depth, there's height and width. Height and width is retained normally as the image size, whereas depth comes from the number of the filters we are convolving or we are using at the each layer of convolution. So let's start. So it is just a matrix multiplication. So it is basically finding the relation between them. So any typical CNN would have convolutional layer, which consists or comprises of the filter matrices. So as I told you, more than uh, one filters is used to each layer. Normally, as a general thing, it is the number of filters are powers of the two, and for image processing, typically they vary between 32 to 1024 filters in a particular layer. Then there are strides, padding. We'll come to these things just in the lecture subsequently. Then ReLU, it is a nonlinear activation function. We already know that that is being used. Then there's a pooling layer. As of now, just understand, pooling layer is for reducing the spatial dimensions of the image. Flattening is required to put them into a single layer so that we can as a 1D vector so that we can actually connect them to a fully connected layer. And finally, there is the activation function for the classifying whether the image has been labeled correctly or not. Under any uh, CNN, multiple convolutional layers followed by ReLU and the pooling layer are there. And we have flattening, single flattening layer. And yes, even fully connected layers, they can be more than one, depending upon what is our image size, what are the applications, what is uh, the properties or the features we have extracted. So the purpose of the fully connected layer is to move towards classification, whereas the set of convolutional layers along with ReLU and pooling, the motive is feature extraction. So convolution, it can happen along single dimension, 2 dimension or 3 dimension. This is the typical formula of your convolution in a single dimension. That is, we have a function f and there is another function g. So that this defines the convolution which is there. So typically f is representing input and kernel or the filter, convolutional filter, a single filter, it is represented by g. So single ka example is all the time series because we have the single dimension of time along which our data is changing. Typically not the images. Images, they start with 2D convolution. And for the colored images, we have the 3D images also. So this is, we come to the pictorial representation of what is a CNN. So yes, we have an input image of any n cross n size, you can say. So this is the first convolutional layer in which the height and the width, they are maintained. And here, single filter, it is extracting and mapping into another matrix in the subsequent layer. So number of filters. Now this depth, it is coming from the number of filters which are being used in a layer. So if I have 7 filters in a layer, means height and width, they remain same, but the depth, that is coming from the number of filters which are, and each filter is giving the output as a feature name. Okay. So let's say if it is a colored image. So, and there is a filter. It means that filter will have 3 dimensions, red, green, and blue. And all these three would be summed up together to make a single feature map in the single, you can say, tensor or the unit in that feature map. And for every filter, this would follow. So I would have, if 7 filters are there, 7 such feature maps would be there, which comprise the depth in the next layer. So there is an ReLU function, which is applied for the nonlinear activation. Then there is pooling. Pooling is actually to reduce the spatial dimensionality. So when I want to reduce the number of features, it is for that. So I cannot, there may be number of features in the image. We don't have to focus on every feature for our application. Suppose it is handwritten character recognition. There I may not require the sharpening or enhancing or so many other features or every background. I just need to identify the black and white so that I can understand where my edges are there. So that is more important. So again, the set is applied. So number of such layers may be applied till we are going to get a manageable size, which can be flattened into a single dimension. On this, we are going to apply my fully connected ANN layer for classification, and we have softmax for multi-classification or sigmoid for binary classification in this case. So we can see that each layer there is a volume which is getting transferred. Volume because of number of frames at the each convolutional layer. So how the convolutional layer actually it is functioning. So here it is by, as of now we are just understanding this in the background, light blue and with the border of zeros, zeros. This is my input matrix, and this is my kernel filter matrix for a single filter which is applied. Let's say it is my, let's go to the previous slide. It's just my uh, filter, I can say. Sobel filter, I can say, though this is not the matrix for that. I'm just telling you that is one edge detection filter. So I start with traversing or mapping of this input image with my kernel filter from one end, and I move across step by step. When I move, the step which is there, like this is covering cross three kernel is there. I don't have the whiteboard. Chalo. So step by step 3 cross, I move this box to the next, so I can take a jump. I can shift it by one column, and it will be now overlapping this second column, third column, and fourth. Then I jump it by next. It will be covering third, fourth, and fifth. Next, it will be coming to fourth, fifth, sixth. So this will determine. So this jump, what I'm jumping, that मेरा जो kernel है, how much it is going to traverse, in what hops it is traversing. That is my stride. Okay. And जितना मेरा stride होगा, that will determine my size of the output matrix which is there. Okay. We'll come to the formulas for the sizing also. So aim basically क्या है कि मेरा filter एक end से start करे. First, it is going to cover the input image and columns, so that corresponding to every box overlap of my filter and the input image, there's a feature map what I'm getting. Again, it is going to move to the next section of the image depending upon the stride, and I am correspondingly having my feature on this output matrix. So then I start moving row wise until I cover and I reach this last section of my input image, and I have this feature matrix completed. Okay, I hope I am able to get clear on this. Basically क्या करते हैं, starting from this end, अब मेरा अगर stride 1 होगा, मतलब अगर मेरा hop 1 column का है, तो अगली बार जो मेरा ये place होगा, that placing of this kernel would be on second column, third column, and fourth. So accordingly जो मेरा home bar का overlap है, उसके corresponding I'm going to get the feature map on my output matrix. So this is the aim of how we are convolving the filters with the input image. So अगर ये मेरा input image है और ये मेरा filter है, the dimensions of my input image are h cross w, that is height is h, width is w, and my kernel matrix is having fh as the height and if w as the width. It means the size of my output matrix will be w minus fw plus, and similarly the height would be given by the similar dimension. और जो उसकी dimensionality रहती है, that remains same. So if it is RGB 3 है dimensionality, तो वो 3 ही रहेगी आपके output. Now what is the use of this filter matrix? Because हम same filter matrix को सारी image, पूरी image के cross traverse करा के convolve करते हैं, उसका फायदा. पहली चीज, I am distributing the weights, okay, which makes it invariant to translation. When I say invariant to translation, so let's say I have a image, okay, और एक उसकी mirror image है, तो इसका मतलब जो मेरा feature extraction है, that would work equally good on the image as well as the mirror image. It is invariant to what is the placement of the objects in the image. So invariant to the translations which is there. Next is invariant knowledge. So it is traversing it लोकेशन वाइज, तो इसका मतलब वो लोकेशनली उसको इनवेरिएंट बनाता है मेरे फीचर एक्सट्रैक्शन को, सो दैट आई एम एबल टू गेट द फीचर्स which are distributed across the image anywhere. So even if the image, if it is rotated or it is scaled, it is able to get the features out. When we come to the stride and zero padding, okay, first understand if it is the 3 dimensions, that is RGB. तो क्या होता है, अगर 3 dimensions है तो मेरा ये कर्नल फिल्टर है, मैंने सेम फिल्टर आई विल अप्लाई अक्रॉस रेड, ग्रीन एंड ब्लू, तीनों में से कोई फीचर मैट्रिक्स आ गया मेरा, उनको I will sum it up, I'll get the value. Let's say 19 is the value I'm getting here, 21 I'm getting it here, 10 I'm getting here. So जो मेरा आउटपुट मैट्रिक्स है उसमें इस फिल्टर के करस्पॉन्डिंग वैल्यू क्या होगी, 19 plus 21 plus 10 plus 1 for the bias. So in this case it comes on to be 19 plus 21 is 40, 40 plus 10 is 50 plus 1 for the bias 51. So feature map the value would be 51 for the single filter across the single section of the image. So let's see the computation. So this is, let's say, the input matrix 6 cross 6, kernel matrix 3 cross 3. So output की dimensions क्या होगी, 6 minus 3 plus 1. 6 minus 3 is 3 plus 1 मतलब 4. Similarly, for the height also, so it is a 4 cross 4 image, which is correct. And this every element is computed as multiplication. So when it will overlap here, so it will overlap on this section, it will start. So 3 into 1 plus 1 into 1, this plus 2 into 1 column wise, then 0 into 0, 5 into 0, 7 into 0, next, and then we have 1 into minus 1, 8 into minus 1, plus 2 into minus 1. So this gives the value to be minus 5 for the first element. So this is first element is my feature map which is there. Okay. Likewise, we complete it as we slide my filter matrix across the input image, first column wise, then row wise, till it reaches the end of the input image matrix. So this is the example of the vertical edge detection using the filter for vertical edge detection. So this is typically the filter, kernel filter for vertical edge detection. So this is by image. So let's say the image is having the contrast of gray and white. So this is having the higher values of the image pixels, whereas for gray it is 0. So when I'm doing the vertical edge detection filter, it is moved, I will actually identify this area, that is where this vertical edge detection is done. So the area which is having the values, positive values, that means that is where we are having the features what we are interested in. And here we are able to detect the edges. Okay, so where it is 0. So it means this section is extracted. Similarly, for the horizontal edge detection, so here the convolution is across the central part of the image. Now my image is such that my white region is across, or the brighter or the positive values are diagonally across these matrices, where other it is grayer at the gray part. So this is by horizontal filter. So what the output I would get from the central overlapping is this. So these are the commonly used filters. We are talking about detection only. So there is a vertical edge detection, horizontal, Sobel. This is again a gradient based. This is also the first derivative based. edge detection filters. So we should know these. So now with let's say convolution एक layer के अंदर we have number of filters. So let's say this red one is defining one filter, green is defining another filter at the same layer. Like I told you earlier कि 7 filters हैं convolution layer में. तो इसके feature maps इसके layer में map हो गए. So इसके feature maps green वाले इधर map हो गए. तो अब मेरा जो ये D है, depth है, ये volume जो मुझे मिल रहा है वो मिल रहा है because of these filters which are applied, number of filters which are applied, and typically they are in the powers of 2, somewhere between 32, that is 2 raised to power 5, 2 raised to power 10 के बीच में typical होती है. Small question. Consider an image of the size 48, 48 cross 3. Kernel matrix is 5 cross 5, and 10 filters are there in that layer. What is the output size of the output feature line we are getting? So dimensionality 3 रहेगी उसकी, और उसका size क्या हो जाएगा? 48, 48 retained, height and width retained, plus depth 10 comes from the number of filters. Whereas the dimensionality remains 3. If it is a colored image with 3 dimensions, it will remain with that. So इसका मतलब ये जो मेरे 10 filters है वो तीनों रेड, ग्रीन और ब्लू के क्रॉस अप्लाई हो. ठीक है. Next, what are the hyperparameters for these filters? The hyperparameters are typically the filter size. Yes, that is very important. Odd choose करते हैं हम. Okay. And they have the depth dimension. I already told you. That depends upon the number of the filters. Then the count, कितने filters लगाने हैं. So जितने भी filters ज़्यादा हो, yes, feature extraction is better because each filter is representing a feature map which is we are getting. But too many may result in overfitting. So we have to start with initially a lower number, and ideal policy is to progressively increase the count depending upon if we are getting the results in my image. Then stride is typically jumping one column and one row, or 2 columns or 2. And as we introduce the stride S, this is how it affects my size of the feature map or the output, where P denotes the padding, N denotes the dimension of the input, and S denotes the stride, either 1 or 2, whatever is the value. And padding, why do we do padding? Padding actually, in this image we saw, yes, we are having the border of 0, 0, 0. This is called padding. Now, why do we even need padding? Yes, it is for saving the information or retaining the information. अब होता क्या है, हमने देखा कि जब हम ट्रैवर्स करते हैं विद फिल्टर है, मेरी डायमेंशन रिड्यूस हो रही. 6x6 की इमेज थी, 3x3 का फिल्टर लगाया, साइज क्या आया 6 - 3 + 1, ये उसकी डायमेंशन रिड्यूस होगी, 4x4 का बन गया. तो मेरी इमेज का डेटा लूज हो जाएगा, ऐसे इट विल बिकम वेरी स्मॉल by the time we are applying number of layers. So we have same padding which preserves the size of the image. So in this we are going with the 0 so that output पे कोई नया feature नहीं introduce हो रहा जब हम उसको convolve कर रहे हैं, but it is retaining the size of the image. Okay, it is not reducing. Valid padding का मतलब है मेरा output feature size कम हो जा रहा है, जो अभी हमने देखा 6x6 रिड्यूस हो जाता है 4x4 में. सो वैलिड पैडिंग के साथ दिस इज द आउटपुट feature map की dimension, and with same padding or the 0 padding, this is the dimension. Okay. So अगर हम stride S लगाते हैं and there is no padding, this is how the size of the output image. NC is the number of convolutions. So that remains same, that is not changed. 10 filter है तो 10 ही रहेंगे. And if padding and stride both are used, this is how my dimensions they are going to get changed. Then we come to railing. The purpose of railing is to actually introduce nonlinear activation to convert negative values to zero. Why do we even need that? First thing is most of the features or the gradients across the image, they are not non-linear only. So with linear, we are not able to have the correct mapping. We can use other uh, non-linear activation also, just like leaky railing we can use, gradient based railing we can use, but this is the most preferred one. And second, it helps to alleviate the vanishing gradient problem. Vanishing gradient problem, it is very important problem which comes with the sigmoidal activation functions. Because sigmoidal के अंदर जो मेरा output आता है, that is limited by some value which is between 0 and 1. Okay. So जैसे हम उसको over the time लगाते रहते हैं number of combination layers, उसका partial derivative it becomes so small that it eventually comes to 0. Like 0.25 अगर मेरी वैल्यू है तो अगर मैं उसका डेरिवेटिव लूंगी I will find the square and you can see the value will come down to point somewhere around 0.1. So 2-3 days के बाद वो 0 के पास हो जाएगी वैल्यू. So there is the problem, the vanishing gradient problem. So if I'm using a non-linear activation function, this doesn't help. Then we come to this next layer, that is pooling. Pooling is actually when we want to reduce the spatial dimensionality because मुझे सिर्फ important features को ही retain करना है. So there are different ways to it. Commonly used are max pooling and the average pooling. Max pooling again मैं इसको uniform matrices में divide कर लेती हूँ. Generally 2x2 हम use करते हैं. जो भी मेरी dimensionality है pooling matrix की, by that factor my each dimension is reduced. Okay. So अगर height मेरी h थी तो मैंने 2x2 यूज किया तो height will become h/2. Width will become w/2 and overall the size will reduce by 1/4. Okay. So max pooling भी जब हम डिवाइड करते हैं इसको यूनिफॉर्म मैट्रिसेस में तो इस सेक्शन में जो सबसे ज्यादा वैल्यू हाईएस्ट वैल्यू होगी दैट इज टेकन एज highest value of that particular feature or filter in that region that is retained. Average may I find the average of it, I sum it all and I divide by 4 and I retain the value. Similarly, sum pooling may I retain it directly, the sum of all the values. Global pooling is used for the larger images जहाँ पे पूरी image के लिए वो लगाते हैं. एक पूरे section के ऊपर I'll use pooling. Rarely used. But yes, it exists. Definitely, it helps you overcome the computational complexity, but it also helps reducing the overfitting. And whatever variations are there, my model becomes more tolerant. So once pooling is applied, if m is the dimension of the pooling matrix, so 2x2 में m की value 2 होगी. So this is what the size of my image is there. So height is changed, width is changed. Yes, convolutional dimensionality remains the same. That is number of filters, number of convolutions they remain same. Then finally we have the flattening layer. Flattening is simply जो 3D है उसको 8D में I lay down because I have to put it across a single. I have to connect with the neurons in the single fully connected network like ANN. Fully connected network जैसे ही आता है इसका मतलब I'm ready for the classification. We have done the feature extraction and now it is typically like a layer of MLP, a multi-layer perceptual model. Okay. So same वही back propagation वाला concept use होता है. So and finally I have binary classification. I have the sigmoidal activation function and for multi-classification I have softmax. So now we come to what is the similarity between CNNs and ANNs. Same structure, we are using back propagation only for learning. For the gradient calculation, वही मेरा use होता है मुझे error को वापस भेजना है. But यहाँ पे मेरे जो neurons है, they are sharing the weights across a region rather than a single to single mapping from input towards the hidden, eventually towards the output in the ANNs. Okay, so मैंने sparsity introduce कर दी, मैंने one to one networks connections की बजाय regions को map कर दिया, जिसमें मेरे वो किसी feature के जो weights है वो shared है. Feature क्या है वो depend करता है filter matrix क्या use किया है हमने इसमें. So pictorially, we can just see that. So this is by feature the kernel. So these rows of mapping, they are indicating according to the kernel which is there. So we are getting the result of this convolution, and eventually with pooling, we are reducing the dimensionality of the features to 2 only. Okay. So back propagation, it happens just like in ANNs. पर back propagation में वही gradients calculate होते हैं जो मेरा एरर है, मतलब जो मेरी क्लासिफिकेशन हुई उसकी लेबल्स में जो डिफरेंस है उसका एरर विद रिस्पेक्ट टू पर्टिकुलर पिक्सल का जो वेट है कर्नल के अंदर, उसके विद रिस्पेक्ट हमने उसमें ग्रेडियंट कैलकुलेट किया. अब वो जो एक भी वेट चेंज होता है, दैट सिंस बाय कर्नल इज मूविंग अक्रॉस द एंटायर इमेज, इट मींस इट इज गोइंग टू इफेक्ट द एंटायर इमेज. सो वो एंटायर इमेज के क्रॉस ट्रेवर्स करता है तो उसके कुछ ग्रेडियंट्स कैलकुलेट होते हैं. वो ग्रेडियंट्स अगेन दे आर मैप टू द इनपुट बाय दिस कर्नल values. Same color coding is used to understand which gradient is mapping to which layer according to which filter. Okay, so this was all for this lecture. Next we're going to start with the first convolutional and neural network layenet which was introduced. So we'll learn about that in the next lecture. So this was all about CNNs. I hope it helps. Thank you so much.